Okay, so in this video we're going to start to look at electrochemistry as it relates to a general chemistry level class. So we'll start with looking at the force on a charged particle. So electrochemistry, the way we'll present this is ultimately we're going to get to cells and different types of cells, galvanic cells and electrolytic cells. But the first thing I want to start with is what is a potential, because we're going to look at the potential of cells, but I think a mistake that is easily made is you overstep what a potential actually is and you just start to calculate the potential. So then you have people that can get an answer, but they don't know what the answer necessarily means. So we're going to start by looking at the force on a charged particle. So let the force F on a charged particle E, let the force F, we'll say it's a vector, so it's a force in a specific direction on a charged particle. E, where E is, to be honest, it's just going to be the electron. It doesn't have to be an electron. We could just call it Q for a generic charge, but we may as well call it E because that's the specific charged particle we'll be interested in. In an electric field, E be given by F is the product of the charge and the field. Let's call this equation 1. So if you've seen my video on Joseph John Thomson's cathode ray tube experiment, then you'll have seen this equation before. If you haven't, then essentially we're just saying that an electric field is a vector field and it influences any charge. Well, the electric field influences the electron and it will apply forces to the electron based on its presence within the field. So we can see that the force applied to the electron depends on the field, or the force, the electric force, is the product of the charge in the field and the field itself. So intuitively the equation makes sense. So electromagnetic theory states that a static electric field has no curl. So if you're not sure what curl is, go back and look at a previous video I did looking at pre-electrochemistry, where we showed that curl, we showed mathematically what a curl is. Essentially for now it's just a rotation. So if I thought that a field had the property of a curl, I could put a test probe in and the test probe would start to rotate and that would be evidence that there was a curl. So for example, if you suspect a whirlpool in a body of water and you drop like a cork into that whirlpool and you see the cork turn around, you'll be validated that indeed there's a curl in that pool of water. So imagine now the pool of water is an electric field and you've got the curl of the electric field. So electromagnetic theory states that a static electric field has no curl. Now, again in the previous video we've said, so I'll just say recall because I'm recalling a previous video, the pre-electrochemistry video. Recall that the curl of a gradient is 0. So the curl of a gradient, del cross the gradient is del A. So del multiplied by the vector A, take the curl of it, the del cross, that's 0. So that's words, that's a mathematical expression. Again, this is in a previous video. So this is a statement, this is a recollection. So it tells us something about how we can view the electric field. So if the curl of a gradient is 0 and the curl of an electric field is 0, then it would be reasonable to assume that the electric field is a gradient. Okay? Again, the statement, if the curl of this object is 0 and the curl of this object is 0, then this object is probably the same as this object, or at least we have evidence, we don't have any evidence to say otherwise. So we're going to state that the electric field itself is a gradient, and recall that a gradient is a slope, and ultimately forces connect on slopes. Okay, so I'm going to clear the board and we'll get on with the next part of this video. Okay, so we've cleared the board a bit. We're just going to restate what we had on the previous screen. So we had equation 1, the force, or the electric force, because we're interested in the electron. The electric force is a product of the electron, or particle, the electron, in its electric field. We then recalled that the curl of a gradient is 0. We recalled that an electrostatic field has no curl, so the curl of an electrostatic field is 0. The curl of a gradient is 0, therefore the electrostatic field is a gradient. So the curl of the gradient of our electrostatic field is 0. Okay, so there are two statements. We're going to take equation 1 and then we're going to multiply by dx. Where d just means difference and x is position in the x-axis. So we're going to look for a change in the x-axis. So we've got f dx equals e arrow dx. We'll call that equation 2. So here we've dotted through, we've taken the dot product. Why did we take the dot product? Because we're looking at vectors and an angle of rotation would be important. Whenever an angle of rotation is important in a product, you should take the dot product. But all we've done is multiplied both sides by dx. We did it via the dot product, again, because we have vector fields. And we've relabeled that equation, equation 2. Now, I'm going to make an assumption. It can be a recollection if you know it, but let the change in potential energy by dx, this is just a definition. So by definition, potential energy, which is position sensitive, the change in the potential energy with location is a minus force. This is just a definition. So we've got the change in potential energy. If we were then to multiply both sides by dx, we'd have minus f dot dx. Let's go ahead and give it a reason to be a dot by putting an arrow here. So I've just multiplied both sides of this definition by dx to bring the dx up here. And I've got this expression here. And I can see that this expression here is exactly the same as this expression in equation 2. So I'm going to go ahead and sub that in. So again, I'm going to take this and I'm going to insert it in here. So we've got the change in potential energy, which is this expression here, is equal to E E arrow dot dx, and I'm going to call this equation 3. Okay, I'm now going to make another assertion as we go down towards something that's going to ultimately be useful to us in electrochem. I'm going to say let the change in potential energy equal between two objects. So let's say I now have two objects that become aware of each other. Let's call them particle A and particle B. So let the change in potential energy between two objects be the potential energy of B minus the potential energy of A. A and B could just be final and initial, just labels to differentiate this versus this. The difference just literally means the difference between two potential energies at two different locations. So if we allow that to be the case, and this implies that the change in potential energy now, if I want to ultimately everywhere in this electric field, it's a product of location, so it's location sensitive. But if I want to get a handle on all of it, if I want to sum over all of those changes, and only the vector is going to be sensitive to the location, so I can get the constants to the left of my integral sign. So the electric charge, let's say, won't change. That's a constant. I do have a minus though. So I think I've lost a minus. I've lost a minus, yes. So here I had f dot dx and here I had minus f dot dx. So I need to go ahead and make that minus. So hopefully that's not too confusing. I lost that minus that was actually present over here. But luckily we caught it before we went too far. It's a constant. It just means minus the same constant. So it's a definition at this point. So minus that, and then I'm going to sum between final and initial locations B and A from over here. So my final minus initial. The electric field as location changes dx. Okay, so I'm going to box this just because we've got lots of equations and it's nice to figure out which bits are with which. So we can just take a look. We've got this E arrow, which is F. I've got minus F in this case because I converted it. I used this expression here, change in potential energy. The dx went over here, which is over here. So with a little bit of inspection, you can see that everything looks okay. Now this integral is going to act on that differential and cancel it out. And we can do that. Initially though, I want to bring this E down here. So I've got this constant E down here. I'm going to essentially divide both sides of this expression by the charge. So if I divide by that constant E, so not the negative E, just by E, then I've got the change in potential energy divided by the electric charge. I've still got the minus, I've still got the integral between final and initial locations. I've still got the electric field, and I've still got dx. I haven't actually done the math yet, but I've got the sum, that I'm going to sum over these differences here in the electric field. But by phrasing it this way, the ratio of the change in potential energy per unit charge, this by definition is dV, which means a voltage difference. So this is an important definition. We're looking at electrochemistry, and we've suddenly, from first principles, we've got something that we're going to call voltage. We're going to be using voltage a lot in calculations, but it's good to know what we mean when we say voltage. So I'm going to tidy up this board and we'll do a little bit more. Okay, so just to clear the board a little bit, recap where we left off. We said that the change in potential energy divided by the unit charge is equal to minus the integral of the electric field between positions B and A as the position changes, and that's equal to the change in voltage. So we've essentially got the change in potential energy per unit charge is the change in voltage. Well, this implies if we get rid of the changes, that the potential energy per unit charge is the voltage. So we have a definition for voltage. If we look at units of voltage, which are always useful, algorithmic maybe, but also useful. The units of energy are joule. The units of the electric charge are coulomb. And voltage is V. So we've got a definition of voltage, or at least a unit definition. It's energy per charge. Okay, so consider we have two metal plates, and let's say this plate is A and this plate is B, and let's arbitrarily assign plate A a positive charge with respect to plate B, which is negatively charged. Okay, so these are just the labels of the plates. These are the charges with respect to each plate. And let's say the plates are separated by a distance d. And by definition, the electric field always flows out of a positive charge. It diverges from a positive charge, and it diverges towards a negative charge. So if we've got a positive and a negative plate, the electric field, which is a vector, is going to point diverging away from the positive plate and diverging towards the negative plate. So this is a source, this is a sink of the electric field. So the electric field lines would flow that way. And let's start breaking this down and learning some things about this setup. We can say that the voltage on the plate B minus the voltage on the plate A, so the differences in the voltages between plates A and B, well, that's the change in the voltage. That's the change in the voltage. We said that that is the change in the potential energy per unit charge. We said that that is equal to minus the sum between B and A of the electric field dx. Okay. So we can say that this is equal to minus the sum between B and A, the electric field. Now it's a dot product, remember, because angles become important, the orientation of these plates with respect to the electric field. So cos 0 degrees dx. So the del dot is just, sorry, not the del dot, that's divergence. The E dot, the dot tells us we have an angle. So we've got cosine. So by definition, dot is cosine of the angle. So we've got E vector field cos 0 degrees dx. Okay, so we can say that let's put it over here. This is equal to minus the integral between b and a of E dx. So cos 0 is just 1. So we've just got E multiplied by 1 multiplied by dx, which is just E dx. So implies that dv, which is what we had initially, is equal to minus E ba dx which is equal to minus E d, where here d is the difference between these plates. It's the change in position, which was represented by dx. So we've concluded that this angle is irrelevant now, so we can go ahead and collapse the dot product into just the regular product. Okay. And the angle is 0 because the plates are exactly perpendicular to the field. So that's why the angle is 0. We'll see another example later on where the angle won't be 0. Let's go ahead and call this equation 4. So let's rewrite it and call it equation 4, and then I'll have to clear up the board a bit. So we've got dV, the voltage difference, at least in this setup, is minus ED. Let's call that equation 4. We'll clean the board and then we'll say some words about this event. Okay, with a slightly cleaner board, we can continue. So we've just left off with equation 4. The change in voltage between these two plates is minus the product of the electric field and the separation between them. So it's a product of that kind. Let's also remind each other of a previous equation. So previously we saw that the change in potential energy is the change in voltage times by the electric charge. So recall that we had the electric charge down here. Now I've just brought it over here so that I can essentially introduce this equation into here. So if I combine these two, then essentially I have the change in potential energy. The change in potential energy is equal to dV, where dV is minus ED multiplied by E, or I can just stick the E in here. And let's call this equation 5. And again, a lot of these equations are just recycling over. We know that EE is just the force. And recall from just basic principles that energy is force times by distance in terms of units, dimensional analysis units. Okay, so we just have another way of looking at a common definition. but we've learned something. Notice this is a positive change in potential energy, and this is a negative charge. So we've learned that a positive change in potential energy is proportional to a negative charge, and we've learned vice versa that a negative change in potential energy is proportional to a positive charge. So this is important, and it just comes out of processing these equations. So what does this mean? It means that the electrical potential energy decreases when a positive charge moves in the direction of the electric field. So the electrical potential energy decreases. There's a negative change in the potential energy when a positive charge moves in the direction of the electric field, and vice versa. The potential energy would increase when a negative charge moves in the direction of the electric field. Okay. Ultimately, this will give us a feel for why electrons move when we start to look at cells in electrochemistry. And I think this is an important part as we begin to broach the subject of electrochemistry for a general chemistry audience. Okay, and finally we move on to look at a situation that's going to help us when we look at batteries, for example, in electrochemistry. We've got a basic graph here of change in potential energy shown on the y-axis. The x-axis could be time. It doesn't really matter, it's less important, but let's say it's time. We have an electric field applied between two plates. A is the plate that has a positive charge, B is the plate that has a negative charge. And I know that the electric field flows from the positive plate to the negative plate. So here it's flowing upwards. And if I put a test particle here, let's say that test particle is an electron. Well, remember, an electron is going to be attracted to the positive plate. So I know that the electron is going to go that way. Now recall from our previous discussion that we said that the electrical potential increases when a negative charge moves in the direction of the electric field. So the electrical potential increases when a negative particle moves in the direction of the electric field. We have a negatively charged particle moving in the opposite direction of the electric field. So we've got the situation where the change in potential energy is decreasing because we have a negative electron moving in the opposite direction of the electric field. And this is favored. So this will happen. So recall our equation 4, I believe we called it, from the previous slide, where we had the change in voltage is minus the electric field dotted with the integral between locations B and A, the change in position, and we said that this was minus E d. I believe we call that equation 4. So if we multiply through by the charge on the electron now, so multiplied by minus E, essentially we're going to do that to make this force. Sorry, not minus E, just regular E. It's the charge that's minus, not the fact that it's a minus object. Then we've got the change in voltage by E, which we know is the change in potential energy, okay, which is our axis here. So the voltage difference multiplied by the test particle between the voltage differences. Well, this is now going to be minus E E d, which is just the electrostatic force times by the separation of those plates. You would dot through if the angle were relevant. Here the angle is 0, so it would just give us a factor of 1. But if this were twisted, any of these plates were twisted with respect to the field, then you would probably put that dot product back in again. Okay, so I think this is some reasonable background to electrochemistry. I'll clear the board and just make some final remarks.